Hello, welcome to another module in this massive open online course. So, we have looked at the least squares paradigm. Let us look at its analog or a counterpart or something that interestingly related to that, which is known as the least norm paradigm, and that can be described as follows, and these two always go hand in hand. This is, so far we have seen the least squares paradigm. What we want to do now is the least norm framework, and this can also be used for signal recovery. Or you can also think of this as signal estimation. Okay. And the least norm paradigm is as follows. So, consider the following problem. Wherein we have again y bar equals a times x bar, and A is an m cross n matrix similar to what we have seen previously. But while previously m is greater than n in the least squares framework, we will consider a framework where m is less than n, that is the number of rows is much lower than the number of columns. So, if you look at this, it will look like this, which is this is your matrix A, this is your vector x bar. This implies that number of rows is much less than number of columns. One can call this as a wide matrix. Just like when your number of rows is more than the number of columns, we call that as a tall matrix. Okay. Remember, previously in the least squares we had a tall matrix. Okay, number of rows is more than the this is number of rows is more than the number of columns. Now we have a wide matrix, that is number of rows, that is m is less than the number of columns. Okay, which basically implies number of equations. So, remember, this is the number of rows, each row is an equation. Remember, row equals equation, and each of this is an unknown, each element of x, because x is the unknown signal, you can say is unknown. So, each so column, you can say each column of A corresponds to an unknown. Okay, so rows equals equations equals m, columns equals unknowns equals m. So, this implies that for this kind of system, when m is less than n, this implies that number of equations is smaller than number of unknowns, which implies that system is under determined. There are not enough constraints, under determined, not enough constraints. Implies not enough constraints on x bar. And when the system is underdetermined, that is, there are not enough constraints, not enough equations, there are only m equations but n unknowns. This means that typically there is no unique solution, or typically there are more than one possible, there are an infinite number of solutions. This implies typically, again let me qualify this, typically with very high probability, typically more than one solution or infinite or an infinite number of solutions. Now therefore, how to determine, now therefore there is an infinite number of solutions, infinite number of possible solutions. So there are fewer constraints, right? There are fewer constraints on x bar, okay. And therefore, how do you determine x bar, which means you have to additionally constrain x bar. Naturally, if there are fewer constraints, the only way to fix x bar or determine a plausible value of x bar is to introduce additional constraints, okay. So therefore, to determine x bar, one has to introduce additional constraints. One has to introduce additional constraints, and therefore one such typical constraint is to find the energy efficient solution, or if you look at norm x bar, minimize the norm of x bar. So this is your additional constraint. Which basically minimizes the energy of x bar, which implies that the solution is energy efficient, implies you are trying to find an energy efficient solution. That is, what does it say? Out of all the, so remember we said it has infinitely many solutions, alright. X bar is not unique, infinitely many possible values of x bar, because it is an underdetermined system. Out of all these x bar, find the one that is minimum norm, that has the minimum energy. That is the solution that we desire, and that is how we are constraining this problem, and this is precisely known as the least norm problem. So this means out of infinite solutions, find the one that has least norm. So therefore this is known as the least norm framework. Least norm or minimum norm, least norm, you can also say min norm, least norm. Previously the previous one was least squares, remember we had no solution. So find the one that minimizes the approximation error, y bar minus ax bar or y bar minus hx bar. Here we have more than one solution, we have infinitely many solutions. So find the one that has minimum norm, okay. And I think I am using the matrix A, and it is fairly straightforward, and therefore the relevant optimization problem for this least norm solution can be formulated as follows. The relevant optimization problem for this is, as we already seen, the objective function is to minimize norm x bar, and the constraints now is y bar equals a x bar. And you can also justify this minimum norm as that naturally occurring signals do not have an infinite amount of energy, they are typically limited in terms of energy. So therefore we want to make sure that the signal corresponds to something that is naturally occurring, which means its energy is bounded, okay. So this is justified because naturally occurring signals have limited. In fact, we will see an interesting version of this later, where naturally occurring signals we will say have sparsity, they are naturally sparse in nature, but for instance to begin with, let us look at the minimum norm solution. In fact, this is the minimum 2 norm, okay, and this is basically this linear system, this is your constraint. So minimum norm, that is the objective, so this is the constraint for our optimization problem, and this can be solved as follows. So what I can do is I can write this equivalently. Solving this is fairly straightforward. We can use the earlier techniques. Minimum norm x bar square subject to the constraint y bar equals ax bar. Therefore, one can form the Lagrangian, which is equal to objective function x bar norm x bar square is nothing but x bar transpose x bar plus lambda times ax bar minus y or y minus ax bar minus y bar. In fact, this has to be lambda bar transpose. Remember, because how many constraints you have? You have m constraints. Each row is an equation, so there are m equations, so m constraints. So there has to be one Lagrange multiplier for each constraint. So your lambda bar will in fact be a vector. Okay, so that is basically lambda bar. So this is one Lagrange multiplier for each constraint. Okay. There is one Lagrange multiplier for each constraint, and now when you take the gradient of this, so your f equals x bar transpose x bar plus lambda bar transpose ax bar minus y bar. Now you take the gradient. We have done this before. X bar transpose x bar is nothing but x bar transpose I, identity times x bar, so this is twice x bar plus lambda bar transpose A into x bar, this is C bar transpose x bar. So the gradient of this is C bar, so this will be A transpose lambda bar, A transpose lambda bar minus lambda bar transpose y bar. Gradient with respect to x bar is 0 and this is equal to 0. Setting gradient, so you are setting the gradient equal to 0, and once you solve this thing, this implies you will get something interesting. This implies that x bar equals minus half A transpose lambda bar. Remember, lambda bar is a vector, so I cannot simply get it or manipulate it otherwise. So I simply have to write x bar equals minus half lambda minus half A bar transpose A transpose lambda bar. How to determine lambda bar? Use the constraint. This is similar to what we have done. To determine lambda bar, use the constraint. Remember, our constraint is A x bar equals y bar. Substitute x bar, which implies A minus half A transpose lambda bar equals y bar, which implies minus half A transpose lambda bar equals y bar, which implies that lambda bar equals minus twice A transpose inverse into y bar. So this is basically, so if you call this as 2, this is the expression for lambda bar, and if you call this as 1, now what we are going to do, substitute lambda bar from 2 in 1. And what we get here is that lambda bar equals, we already seen this, x bar equals minus half A transpose lambda bar. Now substitute lambda bar minus half A transpose minus 2 A transpose inverse into y bar. So the minus half and minus 2 cancel, so this will be A transpose inverse into y bar. This is your x hat. or your signal estimate that has the least norm, correct. So, this is basically your least norm. What we have obtained is the least norm. This is the least norm signal estimate, and this is also known as the least norm solution. So, you can write this as x hat equals A transpose A transpose inverse into y bar. Okay, so this is also known as the least norm solution. Or minimum norm, you can also, there are many names, so this is also known as the least norm solution. Alright, that gives you the solution x hat which has the minimum 2 norm. And as I already told you, this is suitable or well suited for scenarios where there are, it's an under constrained system, that is you have fewer equations than unknowns, you have more unknowns, which means there are infinitely many possible solutions. So, you have to constrain, you have to introduce additional constraints. We want to find the solution, the one which has the minimum norm or the minimum energy, and this expression gives you a closed form expression for the minimum norm solution. Alright, we will stop here. Thank you very much.